Hi everyone, I'm going to talk about multi-criteria shortest path. This is a common work with Nicolas Anus and David Dijkstra. A quick reminder about shortest path. You got a graph with real positive weights on edges, and you want to go from S to T using the shortest path. The weight of path is just the sum of its edges weight. So here the blue path has a weight of 8, and it's actually a shortest path. Here the important thing to notice is that there could be several shortest paths, but there is exactly one minimal weight. In the multi-criteria setting, the weights on edges are d-dimensional vectors. So here I just added a second dimension from the previous graph. So here the blue path is still interesting because there is no path that is smaller on the first dimension, since it was optimal on the previous graph. But the red one is also interesting because there is no path that is better on the second dimension. More tricky, the green one. The green one, there is no path that is better on each dimension at the same time. However, the gray one, you can discard it because the green one is better on each dimension. I depicted the weights of the previously seen path here, and more formally we're going to say that a path is dominated by another one if it's bigger on each dimension. So the green path is dominated by any path in the red zone. However, if there is no path in the red zone, we will say that it's optimal. And as you can see, the gray path is not optimal since it is dominated by the green path. The set of optimal paths is called Pareto set. So here the whole set of dots plus the blue, green and red path is the Pareto set, since none of those is dominated by any other path. It could be computed with a Dijkstra algorithm, however, it's not practical since the Pareto set can be really huge, even exponential in the number of vertices. So we need to summarize it, and a way to do that is to relax the definition of domination with the 1 plus epsilon coverage. So we just added a 1 plus epsilon factor on each dimension. Visually, the green zone is dominated by the green path, and here it is 1 plus epsilon covered. So there is a 1 plus epsilon factor on each dimension, multiplicative factor, okay, for epsilon equal to 0.5. The good news is that you just need 3 paths to cover the whole Pareto set: the blue, the green and the red path. It was proven that you can use a polylog number of paths to cover any Pareto set. However, it's not practical to compute the Pareto set and then to extract the polylog number of paths that you need. So you need to summarize during the algorithm, while discovering paths. And the problem that might occur is that you could end up with non-optimal path. For instance, you can use here the gray path instead of the green to cover the Pareto set. So it works, it covers the Pareto set. But it's not the points that you use, it's not a subset of the Pareto set anymore. So it might be bigger than the Pareto set itself. In order to solve this problem, there is two main schools. A more theoretical approach, with the algorithm from Tsagoris and Zarouliis, with this nice complexity that guarantees that the output is covering the Pareto set. The problem is that it's unpracticable. On the other hand, there is a more practical approach, but these techniques, even if they are very efficient, they do not guarantee that the output covers the Pareto set. So to simplify, the techniques that are used here is more or less that if you got two paths that are very close, you can discard one of those and consider that the one you keep represents the one you discard. Okay? But the problem is that what is close? If you consider that two paths are close because they are at a factor less than 1 plus epsilon on each dimension, it does not work. because the error cascaded. So that's why the practical approach do not have any guarantee. In order to tackle this issue, Tsagoris and Zorgis consider that two paths have to be much more closer than a factor 1 plus epsilon. So that's a reason for the exponent d on the complexity. And another reason it's impracticable is that it keeps some dominated path, but if you remove those dominated paths, then the complexity gets worse. So represent some kind of an in-between with a framework that we call Meta. It works similarly to MC Dijkstra, which I will present later. We instantiate this framework in two algorithms, frame, which is specific for 2 dimensions, and sector, which work for any number of criterion. What is great about frame is that it's Pareto compatible, which means that the output of the algorithm is a subset of the Pareto set, which gives us that the size of the output is smaller or equal than the size of the Pareto set. So, in terms of complexity, here you got Hansen algorithm, which is Dijkstra in dimension 2, and S is the Pareto set size, S epsilon and S epsilon prime are the output sizes. And here, as you can see, it seems like the same complexity, but frame is Pareto compatible, so S epsilon is smaller or equal than S. Then you know that frame's complexity is smaller or equal than Dijkstra 1. For Tsagoris and Zorgis algorithm, the problem is that S epsilon prime is not comparable to S. And for any number of dimensions here, Martin's algorithm is the generalization of Hansen for D general. And as you can see, sectors seem to be better in terms of complexity. However, sector is not Pareto compatible, so we cannot compare S epsilon to S. We did some experimentations on frame using a Brogan protocol with a complete oriented graph with 19 vertices. So it's on the left. And we do some variation to random graph on the right. As you can see, if the Pareto set size is huge, then frame behaves very well because it summarizes a lot. And you can observe the same with time here. It's very efficient when the Pareto set size is huge. But this graph is very specific, so we did some more experimentation on real graphs. So we did it on road networks from the 9th Dimax implementation challenge. The criteria are distance and time, which are correlated, and we did it on every state of the United States of America, and so each dot is a state, and as you can observe, when S, so the Pareto set size, is increasing, it seems that the gain of a frame algorithm is increasing also. So here the gain is the size of the Pareto set divided by the size of our output. And it's even more clear with time here. The gain on time is increasing while the Pareto set size is increasing also. A few words about the algorithm. So here, how does Meta works? So for Dijkstra, you got temporary path and permanent path here. So permanent path, you consider that they are optimal. At first, you just put an empty path from the source to itself in the temporary path, and then you loop. So you start by extracting the minimum in the lexicographic order, so P, okay. You insert it in S, considering that it's optimal, and also you extend it, meaning that you add an edge at the end. Then, if you just add PE in T, the problem might be that It could be dominated by a path in T, or a path in S, or also it could dominate a path in T. So what you do is you add PE in T, and then you remove any dominated path in T, dominated by another path in there, or in S. Okay? We propose two modifications for meta. The first one is that in order to extract the minimum by lexicographic order, we remove the minimum by rank. The rank is just the sum of the coordinates. Thing is that there might be a lot of paths that share the same rank, so you can remove several of them at the same time. The second modification is that you remove dominated path while leaving the temporary path and not while entering as before. So you just need to compare the path P, Q, etc. to the path in S. You don't need to use any more T. The problem of this modification is that you might see more path, but it does not change the complexity, and in practice it's more efficient because the data structure are simpler, way simpler. But I presented the meta framework so that it computes the Pareto set. But we want a summary. So instead of just removing dominated path, we are going to sample. Visually, the meta algorithm works like that. We consider increasing rank, okay? And for the frame algorithm, if you got path of the same rank here on the same line, and the green zone is the 1% coverage of U1, the blue zone is for U4, then you can prove that if U1 and U4 are covering each other, then you can remove any path in between and still get a 1% approximation at the end. So you still cover the whole Pareto set. And the difference between this algorithm and the one I talked about in related work is that here you use two representatives. So U2 is represented by U1 and U4. It got a representative on each dimension. I won't present a sector algorithm, but it works similarly because when you remove a path, you consider that it is represented on each dimension. Okay. So here we presented some new techniques to get a guaranteed approximated Pareto set, but also the Pareto compatibility that is very nice because we only get optimal path in the output, but also it's very interesting in terms of output-sensitive complexity. So the problem here is that sector is not Pareto compatible, so we would need an algorithm that is in a general dimension. And also we would need some experimentations on sector. More general questions. We dealt with static graphs, but what about temporal graphs in order to generalize it to multimodal setting? And also how to use speedup techniques. Of course, in order to improve the query time, but also because what was hidden here is that Dijkstra and Meta are answering the one-to-all query. So you go from one node to everyone. But using speedup techniques, we might be able to answer the more frequently asked queries one-to-one, from one node to another. So thank you for your attention, and if you have any question,